So I was thinking to make an experiment. If you have questions during the talk, maybe you should ask them during the talk. There's no point, if you don't understand something, it might compromise the rest of the presentation for you. So just raise your hand, and I'll try to take them online. And if it doesn't work out, I'll stop you and we'll finish the presentation. But it's more important to understand than to finish the presentation. So this is me. I used to be a researcher most of my life. Now I am a startup founder at this little company called Feldera, where we're actually building the stuff I'm going to talk to you about. So streaming is a very overloaded work. It means many things, the streaming media, the streaming data. We're not talking about streaming media here. We're talking about streaming data. There's a lot of systems in this space. And I'm here to tell you that I think most of the systems will disappear because they will become obsolete based on the technology I'm going to describe now. So today, there's two kinds of systems. There's databases and there's streaming systems. And they kind of overlap to some degree, but they have different capabilities. My claim is that this is an accident of history, and this two will be unified in the future. So both of them compute on collections of data. Streaming systems, they compute on collections of events. By the way, I'm talking here about computation. So I'm focusing on the computation part, not necessarily on the routing or the distributed aspects of, let's think about stream analytics. That's the problem I'm solving. Okay, so streaming systems, they deal with collection of events, whereas tables deals with collections of rows, tables in databases. Then in streaming systems, new events are generated by data sources, but rows in tables can be inserted, deleted, or updated. And as I said, we are doing analytics on streams or on data. I think there's a very large overlap in what you can do. Many streaming systems use custom languages, dialects of Python or Java, or many of them are converging towards SQL or adding SQL capabilities, subsets of SQL or SQL. Databases are standardized on SQL, although, there's many dialects of SQL, but to a large degree, people understand what SQL means. And in streaming systems, what changes frequently is the data. Streams events appear continuously, but the computation tends to be slow-moving, whereas databases have two kinds of computations. Queries, ad hoc queries. You issue a query that runs once, you're finished, you see the result. And views. Queries are fast-changing, but views, you install a view, and then the content of the view changes slowly. So these are two kinds of computations that databases offer. Then state. There's a lot of custom state management in these streaming systems, whereas for database, it's clear. State is in tables and indexes. So these are very mature, very old technologies. These tend to be much newer. And then streaming systems, people build custom streaming systems because they tend to be optimized for low latency. You want to react to streams, to events quickly, whereas database in general optimized for high throughput. You have big tables, you want to run a query, and you want to see the result. You want to process many rows at a time, not necessarily to get the result as quickly as possible. And I claim that in the future, the database will actually eat this whole area. And I'll tell you, we'll have to fill this table, and I'll explain to you how this is done. And what you will get is a unified system. So this one in the middle is this streaming database, let's call it, which can talk to a variety of data sources. Some of them are batch sources, like signified by field arrows. Some of them are streaming sources. And you'll be able to stream data, batch data, and mix and match inputs and outputs at the same time and write computations in SQL. And you won't have to make any compromises for doing that. You'll be able to run arbitrary SQL queries. You will be able to do any mix of data sources, streaming data sources or batch data sources. You will be able to compute on any kinds of changes to your data. They can be insertions, updates, deletes to your tables, because you will only have tables. There will be no streams anymore. Tables and streams, they will be the same thing. And then the key that will make this efficient is the incremental computation. So why database and streams are different is because they are optimized for different regimes. But if, when you see an event, the amount of effort you do to compute the result you care about is proportional only to the size of the change, which is one or a couple of events, and not to the size of the whole data that you're storing, then you can have a low latency database. So this is the ingredient that will tie them together. And you can even do things that might sound bizarre, like, at least streaming data sources, as we heard, you can conceptualize them as an infinitely growing table where you keep only appending and never delete anything. It turns out there are some queries you can compute on such infinite streams using finite memory. So not any query, but some queries can be computed using finite memory. So if you believe I'm just throwing random things around, this is peer-reviewed. This was published in the Conference on Very Large Databases 2 years ago now, and got the Best Paper Award there. And not only, but there's an open source project. You can actually download all the code. We have an open source runtime and the compiler. And you can play with it. It's MIT licensed. So the proof is in the pudding. But today I'm not going to talk to you about what's in that paper. I will tell you, I will try to convey the core of the intuition, because I think this is the most valuable part of that this work. It's you look at systems and streaming systems in a different way than you used to before. And you look at database in a different way than you used to look before. And then suddenly, if you look in this changed way, they become the same object. That's, I think, the most valuable contribution of this work. And I will tell you about 3 important ideas that will change your point of view. I'll tell you about what incremental computation is and why it's the core to making databases run very fast. Then I will tell you what changes are. Turns out that if you don't understand what changes are, it's very hard to compute using changes. And then we'll talk a little about streams. And if you put these 3 things together, what you get is a streaming database. You use the tools that people are familiar with to compute on collections, but the collections are collections of events, not just of tables and views. OK, so number 1, incremental computation. So what is the setting? The setting is the following. We have a database, this cylinder here. And then on database, what do? You run queries. So this blue arrow is a query. You run it on the database. What you get, the result is a table. Significant is this matrix. So as an example, let's take a running example. Let's say your database has some customers, and each customer receives money and pays various amounts. So you would represent, for example, the charges you can represent using negative numbers and the deposits using positive numbers. And the kind of a query you could run, for example, you would like for each customer to know how many funds it has in the bank, right? And in SQL, this you would write as sum of the deposits where you group by customer. If you don't know SQL, don't worry about too much. I think this is intuitive. For each customer, you sum up all the deposits. And because some of the deposits are negative, this will give you an accurate value of what is in the account of that customer. So this is actually a key observation, first of all. You should, if you represent charges and deposits as positive and negative numbers, then you can always use the sum to accumulate them. Remember this idea because we'll reuse it. And the result of such a query is a table with 2 columns. One column is the customer, and the second is the amount available. All right? It makes sense? Now, what we want to do, and what happens is databases change, right? So, for example, databases today tend to be biggish, 1 billion rows. I don't know if you can see because of this lectern. So let's say this database has 1 billion rows. And the database changes because, there's deposits, there's payments. So, but the changes tend to be small. So let's say in one change, you modify roughly 100 rows. And then I'm showing time going from left to right. And I'm using this symbol delta, the Greek letter delta, to indicate a change. Whenever you see a delta, we're talking about a change. So the database keeps changing, right? So for each database, you apply a change, you get a new version of the database. This is how databases work. That's what they do. And then these changes in database parlance, they have a name. They are called transactions. Transactions databases are very nice because they always form a sequence. They are so-called linearizable. So you know what happened before and what happened after. There's a strict order, linear order of the transactions. Now, the problem we want to solve is we want to run this query, and we want to keep the result of this query up to date. So as your database changes, we want to run the query every time the database has changed, and we have a new result. And there is a mechanism in databases, as I hinted. It's a view. The way you do this in any database, you say create view v as, and then you specify the query that computes the view. So this is exactly what happens. The database keeps changing, and every time you have a new database, this query will be rerun, and you will get a new version of the view. Does it make sense so far? All right. Now what we want to compute incrementally. So let's say you have a roof and one tile breaks. You don't want to replace the whole roof. That would be very wasteful, right? So what you want is to find the tile that is broken and replace only that one. So that's what is incremental in a database. For example, in the example we had with the database with customers and funds for each customer, if a deposit happens for a customer, we only want to compute the row for that customer. There's no point in recomputing the values for all the other customers because we know they haven't changed. And this is what is called incremental view maintenance in databases. Don't recompute everything. Compute only what's new. So if you see an event that affects some of the output data, try to only recompute the output data that is affected by that event. So if you look at our previous picture, this is the picture I've shown you. The database keeps changing. Now, instead of thinking about recomputing the view by applying this green query, so we used to apply the green query to each database, what we're thinking about is how does the view change when we change the database? All right? So instead of trying to recompute the view, we try to compute what's new in the view. And then we define a new query, this blue query. We call it Q delta. This Q delta is a very special kind of query because it looks at the changes in the database and gives you the changes in the view. And if you can indeed compute the changes in the view, you apply these changes to the view, and then you always have the view up to date. This is what people call incremental view maintenance, or this is what they should call. This is, in fact, our definition of incremental view maintenance. And I think you should all agree that this is what we want to achieve. And the point is, why do we want to do this? Remember, let's say this database has 1 billion rows, and each change has 100 rows. Then the ratio between these two objects is 10 million, right? So this object is 10 million times smaller than this database. So if the effort to compute the blue arrow is 10 million times smaller than the effort to compute the green arrow, then we have really saved a lot of effort, and we can do this much, much more efficiently. And we indeed, we have a customer, they have a Spark cluster with 60 machines. They have some data. They start running the Spark cluster. It takes them 20 minutes to compute the view. All right, so this green query takes 20 minutes using a large amount of computation. They get the result, and when they are finished with the result, the database has changed in the meantime, so they start computing again. So they run this continuously. Every 20 minutes, they compute a new view. By using this approach, they can do it in about 1 second. So it takes 1 second to compute the changes to the view. So they can always have fresh views. In this approach, in the original approach, they could only have views every 20 minutes. Now they can have a view every 1 second. So you see there's huge benefits to be obtained if you can compute incrementally. Right? So 10 million times faster. That is a lot of money or time. So you can either, sometimes the latency is important. So no matter how much money you spend, you might not even be able to get the result as quickly. So you can either use fewer resources and get the same result, just a second, or you can get the result much faster. Yes? Okay, so so you are asking me what is the 10 million times faster? All right. Okay, indeed. So the first time you compute the query, you have to spend the time to scan the whole database. But then for each update, you hope that the effort done here is proportional to how many objects you have here and not to the number of objects you have here. And this number is 10 million times smaller than this one. So each of these arrows, each of the blue arrows is 1 second. All the green arrows will be 20 minutes. Does it make sense? Okay. No. It goes to the delta. That's the whole point. Because this could also be a big object, right? If you have 10 million customers, you would compute 10 million rows. But here we only compute the one row that changes. That's the one we patch. So we patch the view. That's the whole key. Yeah, good question. Okay, now I mentioned these changes, these deltas. Let's look at the changes. What are the changes? So we have to look at changes in a different way. If you have a table, a change could be inserting a row at the bottom, I show it in green, or deleting a row in red at the top. So these are the changes the database accepts. So I'll assume the schema doesn't change. That's a different story. Let's assume just the data changes. All right? So databases understand very well the notion of tables. This is what they are built on. But the notion of a change is much more difficult for databases. There's no built-in object in a database that represents a change. But I claim that changes should be first-class objects. I don't even get to fly first class. Changes deserve that. So what does that mean? And how can you do that? So the change should be the object you compute on. And then because the changes, we wanted to compute from the orange arrows to the orange arrows, those are changes. How can we even represent changes? So this is the first core idea. We call them z-sets. They have a very simple data structure. If you have a table which has rows, so this part here is a table, the normal database table. Just add one column to the table, and for each row, keep a weight. The weight is an integer number, and that's why we call them z. In mathematics, the integer numbers are in the set z. They are called z-sets or z relations. This is a very old idea, so this was proposed 25 years ago at least. So this object is not a bizarre object. It's still a table. It just has an extra column. And this column tells you for each row how many copies of the row you have. All right, so this row, John 12, shows up 3 times. I have 3 copies of it. Okay, so you can compress. If your database has duplicates, this gives you the chance to compress the data. But it also allows you to say, this row shows up -1 times. So what's the point of that? Well, this allows you to represent changes to tables, not just tables. So let me explain. But first of all, let me point out that if you take a normal table, that is also a z-set. It's just a table where each row has a weight of 1, at least if there's no duplicates. So this data structure of a z-set can do 2 things. Can represent both the tables and the changes to the tables. So there's one data structure now to represent the data and the changes. And when a weight is positive, it means the rows are added to a table. When the weight is negative, the rows are being removed. And remember how I told you that this idea to have withdrawals as negative deposits? That's exactly the same idea, but for rows. And it applies to any table with any schema. All right? When you have 2 tables, how do you add a change to a table? You just match the rows that have the same columns and add the weights. That's how it works. So the negative weights are not that bizarre. They are just like the negative deposits. You deposit a negative row. So let me tell you a joke. They bring 3 scientists, and they say there's a house, and 2 people enter the house, and later 3 people come out. How do you explain this? And the biologist says, obviously they reproduce, they multiply, so there's more people. And then the sociologist says, oh, obviously there was somebody in the house. And the mathematician says, if one more person goes in the house will be empty. So z-sets work kind of like that. So you should think of them as representing both positive things that cannot exist or will disappear. But they are a very, very nice data structure. They are tabular, and they allow you to represent changes. And then there's actually a variety of objects in databases that could be represented by z-sets. Let's take this picture. This is a fragment of the picture I showed you before. So let me point out what you can use z-sets for. The z-sets could be all the tables and all the views that you have in a database. The z-sets could be all the changes you apply to the tables, the transactions, and all the changes you apply to the views. Suddenly, we have a data structure, and now we can explain what this blue query is computing on. The inputs are these tables with negative or positive weights. But also, people build data capture streams. Change data capture is a big industry. It's only an industry which tries to guess, given a database, tell you what's new in the database since the last time you looked. You could represent most of these changes, not the schema changes, but the data changes using z-sets. Database logs. In fact, many change data capture streams are extracted from reading the read-ahead log of the database. The database logs indicate what you're going to change in the database before you do it. And in SQL, you have insert and delete statements. These can also be represented using z-sets. Z-sets are a very powerful language to describe what's new in a database. Transactions. A transaction is a collection of z-sets. When you do a transaction across 5 tables, you could just describe the transaction using 5 z-sets, one for each table. In fact, I claim that z-sets should be a standard data exchange format. When you talk to a database, you should send a z-set, and the database sometimes should tell you the answer in terms of z-sets. I'll talk a little more about this. And data lakes, if you look at data lakes like Hudi, Delta Lake, or Iceberg, they represent large volumes of data, but all of them, when you mutate data, they append some change logs. These change logs are in a different format than the data itself. They often use Parquet or similar formats. But for the change logs, they use JSON. There's no reason for doing that. These three, if you are a data lake developer, please listen to me. Use z-sets. This will make your life so much easier because you have the same algorithm for reading the changes and the data, and then combining them is just simple addition. And it also happens to be commutative, so you can do it in any order. If you have tombstones to represent deletions, they are not commutative with the insertions. So I'll talk more about this at ApacheCon in Minneapolis in September if you want to. I'll try to convince you if I can't convince you now. OK. So we talked about incremental computation. We talked about changes. There's a third ingredient that you should internalize to understand why databases and streaming systems will be the same, and that's the stream. What is a stream? A stream is just an infinite sequence of objects. This is time in this picture going from left to right, and this happens to be a stream of integers. But it could be a stream on anything, of events, of changes. So let me show you some streams that I have depicted already before. This is a stream. It's a stream of databases. So I show the first 4 versions of objects in this stream. So people don't think of databasing as streams. But databases are streams because they keep changing, and they form a stream because there's a very well-defined sequence of those changes. And these are snapshots. People call those snapshots. So databases are streams of snapshots. This is another stream. Transactions form a stream. It's a well-defined sequence of modifications to a database. It's a sequence of objects. It's yet another stream. Views. Remember that view, every time the database would change, I would have a different view. This is another stream. It's a stream of view snapshots. And finally, the changes to the view. These are also form a sequence of well-defined objects. Amusingly, all these could be represented by z-sets. So each of these could be represented by a stream of z-sets. So why is this important? Because a stream computation system, the inputs and outputs are streams. And I will show you that databases are already doing a fair amount of stream computation. For example, what is a view? A view in a database, the input is the sequence of database snapshots, and the output is the sequence of view snapshots. That's what a view is. So it is a stream computation. Maintaining a view is a stream computation. The input is a stream, the output is a stream. Now, this is you listening to me. So what happens? I am trying to convey some ideas, some of which might be new to you. What you are perceiving is a stream of experiences. Some of them are visual, some of them are auditory. These streams come to you by events one by one, all right? But what happens in your brain? Think about it. What you're doing is you're listening to each thing I'm telling you and adding it to the things I told you before. So you're building in your brain a database by adding up everything you see, all right? This is actually, in mathematics, this is called integration. So if you don't like calculus, maybe you like it a little more now because you realize that you are integrators. That's how you live. In fact, all the systems that we build, that's how they work. They get a stream of events that they process, and then often they integrate by accumulating information from across all the events in the stream. Where is stream integration useful? That's what a database does. Okay, remember, a database, the input is a stream of changes, transactions. The output is a stream of snapshots. How are these snapshots built? By integrating, right? This database is the one at the beginning. This one is the one at the beginning plus the first change. This one is the second plus the second change, or the same as the first one plus the first two changes. That's integration. Databases are already streaming systems. They integrate all the changes. And we heard today about event sourcing, right? Event sourcing, we heard the choice is between keeping the state or between keeping all the events that produce this state. I'm telling you, you don't have to make a choice. You can have both. The events are a stream, the one on the left, and the state of the database is the integral of the event stream. It's a form of integration. So you can define the state of a database, which is does event sourcing, as the integral of the event stream, and you can maintain it incrementally, and you can have both of them for free, cheaply. And why is that important? Because the event stream, as I told you, can grow unbounded. So consider this example with a bank and some customers. So customers make deposits, payments. The number of customers is finite. So let's say you serve all of the Netherlands or Belgium. The number of customers is finite, but the number of transactions is unbounded because each person will have new transactions every day. So the event stream can be unbounded, but the integral of the event stream can be always bounded. And that's nice, because if it's bounded, you can hope to compute on it much faster and using a finite number of resources. So that's why it's important to distinguish those two and to try to use this one as much as possible. All right, now, let's say after this talk, you meet a friend and they ask you what's new, and you try to describe what happened. How do you do it? You tell them, oh, we met last week. Let me tell you what happened between now and last week. So what you produce is a dual of the picture we had before. You'll verbalize the stream of events, and you'll describe. First I went to the market, then I met John, and so on. So what is this process? You're producing a stream of ideas, words, or sounds, depending on which granularity you look. But how is this stream produced? Well, you're looking at what your mental state was a week ago when you last met your friend and what the state is today. So you're doing a diff between what you told the friend before and what happened since then. All right? So this is differentiating, right? This is computing what's new, computing changes. And this is a stream computation. All right? So this is what CDC, change data capture systems, do. Given a stream of databases, they produce a stream of what's new in databases. So this is also a stream computation. And computing diffs is something that is ubiquitous in computing, right? For example, when you do an incremental backup, how do you do it? You look to see what files are new, and that's the one you save. When you use Git, for example, how does Git work? It takes some hashes of the current and the remote trees and only sends the files that are new. This is a diff. When you use the diff tool to compare two files, you see what's different between those two versions. And finally, for example, this is a snapshot from Microsoft Word, but all the document editing software can show you a diff between documents. This has been deleted, this has been inserted, and this part is common. So diffs are a standard tool that is used everywhere. You should think of computing diffs between streams as being differentiation of streams. And it's the dual process of integration. If you have a stream of snapshots, by computing the diffs, you compute what's new between every two snapshots. So why is this important? Because I will show you now, if you remember, we started with the goal of computing Q delta. Q delta was this computation that tells you what's new in a view based on what's new in the database. I'll do it in 3 easy steps. This picture we've seen before. A database is the integral of a transaction stream. Second, a view is a streaming computation of databases. Given snapshots of the database, you compute snapshots of the view. And 3, given a stream of views, using this differentiator operator, which I described to you, you can compare what's 2 consecutive views and compute what's new. Okay, now look at this picture. What happens is the first arrow is the same as the second arrow, and this arrow, the fourth one, is the same as the fifth. So you can actually hook this up. So if you hook up these 3 diagrams, you get a system. And let's look at the system. The input is a stream of transactions, and the output is a stream of view changes, which is exactly what we said to do at the beginning. All right? So the composition of these 3 operators, which are very simple operators. The first one just adds up things. The second computes a query. And the third one computes differences between consecutive objects. If you compose these 3 objects as a system and implement it, you got Q delta. This works for any query that you might be able to write. Any query you can express here will have a version which is incremental computed this way. So essentially, this is actually a very old problem. In the 70s, you can read papers. It's called the incremental view maintenance problems. And there are many, many papers with partial solutions. They say, if your query looks this way, that's how you do it. Or if your query looks this way, that's how you do it. But finally, now, we have a compiler that works for any query. Any query you can write here, I have a compiler which will generate this Q delta for you in a systematic and very simple way. This is the core value. And this is the incremental view maintenance problem solved, and that's why this will solve this will enable databases to become streaming systems. So if it's so easy, why hasn't anybody done this? It's too easy. It's too, I mean, I haven't shown you anything particularly deep, right? Well, one thing is that databases are designed to think that there's a positive object. And a database, everything exists. You have a table with rows. But this notion of a row that you remove from a database, that doesn't exist. And that's a crucial ingredient, because these computations, they actually all compute on z-sets. All these objects can be both positive and negative. That's very important, because when you remove something in the database, you have to be able to propagate that removal through these operators. And that didn't exist before. All the ideas, these ideas, all of them existed. The idea of integration and differentiation, they come from digital signal processing. They are standard ideas. Just putting them together hasn't happened yet. And then this idea of thinking about database as a streaming system enables you to do some things that you couldn't do with databases before. So I explained to you how you can take an arbitrary query and compute it incrementally. But you can do even more. You can take mutually recursive queries and incrementally update them as the database changes. So we built, for example, a spreadsheet in a SQL, where the spreadsheet is we have a 1 billion cell spreadsheet. It's a demo on our website. People fill cells with formulas, which can depend on other cells, and you want to compute a fixed point. And you can do this using SQL and this capability. Or, as I mentioned, alluded a few times, you can even compute on infinite streams with bounded memory. Some classes of queries work very well. So we built all these capabilities, and they tend to be valuable for different application domains. So the top one is mostly standard database analytics. This is graph analytics, the second one, or many applications in security. And this one looks more like what people think of event processing. But they're all in the same engine. You don't need 3 engines. And who knows, maybe there's more we could do. We haven't had time to think about it enough. So Feldera is a little startup. We are now 8 people full-time. We got funding 2 years ago from some venture capitalists, and we built such an engine. We have an open source compiler, which is built on Apache Calcite, and with an MIT license. And we have a Rust runtime library, which is also open source. And it can indeed operate we have built this diagram. So we are this query engine that can sit here in the middle and can talk to all these data sources and do a mix and match of computations. And it works for any insertions and deletions, and updates are just z-sets. An update is an insertion followed by a deletion, or actually a deletion followed by the insertion. And somebody actually even built an implementation. So the core theory is very simple. Somebody built an implementation in Python in a few hundred lines of code. But if you want to build a high-performance engine that works at very large sizes, you have to do much more work. You could say the same as a Java hash table is the same as a database, like SQL or Oracle or SQL Server. They functionally are the same, but one of them is much higher performance than the other one and works for a much larger data sizes. So that's the difference between the core idea and doing it at scale. Okay, I set up to do a demo. I could show you how this works. I don't know. Would you like to see? Okay, so by the way, you can run this demo yourselves. We have a website, and we have this web-based IDE. In this window on the left, I don't know how big the fonts are. I'm not used to. I only have a trackpad. I don't know how to increase the font. I'm sorry. Control, yeah, but let's see. Control plus. It works. Fine. Great. Thank you. This is Firefox. So, for example, this demo is we just take some TPCH queries. So what you do is you define tables, as in SQL, standard SQL, and then you can write some connectors. So the tables don't exist. Unlike tables in database, they don't store any data. They are just the interface to the outside world where the events come from. So you could say that this is the schema of the events, for example. I have some warnings here. I'll just hide the warnings because they are distracting. So for example, this data comes from some S3 buckets where we saved the standard data set used for TPCH. So I have a number of tables. They are all from a standard benchmark suite. And then we have 10 views here. For example, let's look at one view. So people use this frequently when benchmarking databases. So for example, all right, this is, you say create materialized view, and then you specify a SQL query, which depends on the tables. So these views are also virtual. They will not necessarily store the data. If you say materialized, they will store the data. But in general, they don't need to store the data. They are connectors which will notify you when data has changed. And the system, every time you insert something in a table, will update all the views automatically. And if you say start, this actually will run very quickly because we use a medium-sized data set. So, all right, so this pipeline is running, and here it shows you how many records have been processed. And this has about 860,000 rows, and I think they were processed by now. I don't know why. I think I made the fonts a little too large, but you can see it's processed all the input data. And now there's no more data to be supplied to the inputs, but what you can do is you can interact with the views using a query window here. For example, you could say select count of start from Q0, which is one of the views. And this will run the query. Maybe there's no Q0, maybe there's only Q1. Just a second. Let's see. So the result was 4. It's shown up there. So the result of this particular view has only 4 rows because this is what it computes. But what other thing you can do, for example, is you can insert data in a table. So what I'm going to do, there's a comment here which suggests how you should try this. So I'm going to insert a row in an additional in one of the tables. And here we'll look. So this is the so-called change stream. So you can look at any of the tables or any of the views to see what's new. So let's execute this query. So this inserts a row in a table, and I'm looking at the view Q1. All right, so you can see now that this is a Z set, and it's a +1, and this view happens to have 3 columns or 4 columns, and this is the row that was inserted. And you see it's instantaneous. Although the data is relatively large, it's not huge, it's a large data set. As soon as you insert an event into one of the tables, the event is reflected in the views that depend on it. So all of them would change. So that's roughly how it works. And we have connectors for a variety of data sources, Kafka streams, S3 buckets, Delta Lake, and so on. OK, so I didn't tell you exactly how this works, but there's 3 core ideas, and I think each of them is very valuable in itself. So you might find uses for them. They are very clean and very simple. The first idea is that changes and data, both they can be represented using Z-sets. And the Z-set is nothing but a table where you have an extra column which gives a weight, an integer weight to each row. So a table can represent changes to other tables using Z-sets. And it can represent both positive and negative changes. The second is everything is a stream. Objects that form sequences are streams, and not only events form streams, the databases themselves are streams. The snapshots to database or views, they also form streams. The transactions themselves form a stream. Why is that important? Because if you should think of databases computing on streams. All right, the database is a stream of snapshots. And if you think about this way, then these algorithms that I described, they become obvious. The incremental view maintenance is a stream computation algorithm. It cannot be expressed as a function that works from a database to a view, but it can be expressed as a function that works from a stream of databases to a stream of views. And finally, another very useful tool is to think of incremental computations as consuming and producing changes. Not only consuming, but also producing changes. So now we have finally enough information to fill this column. I can tell you how this streaming database will look. Now, I expect that all database companies will be doing this at some point, and then they will essentially eat the streaming systems. We built a prototype, but our prototype is not a database because it takes 20 years to build a real database, and we don't have the resources. But this absolutely makes no sense not to be in a normal database. Our only chance as a startup is for the database people to be too lazy to read our paper and not to implement it. So until then, we have a chance to take some of the market. OK, so tables, they should be Z-sets. All right? So that's how you unify collections of events and collections of rows using Z-sets. Then, events are generated. So you could think of an event stream as a table where you only append new records. A record is an event. But you can represent this in databases too, and databases can do insertions and deletions. Z-sets will unify insertions, deletions, and append. They can represent all of those. They work just fine. And analytics, you can compute anything you can do on normal sets or tables, you can compute on Z-sets. The math just works fine. So all of the relational algebra, all of the operations in SQL, they compute just fine on Z-sets. So that's how you now can compute both the changes and the tables themselves. And you only need one language. So why do people migrate towards SQL? Because they build custom languages for streaming systems, and these languages are just fine. But suddenly, when they start to need collection computations like group by and filtering and all that kind of stuff, they realize they need a lot of the SQL capabilities. So SQL, for better or worse, it's an ugly language. It's a terrible language. It's a very old language, but it works and people know it. And it has some good characteristics. It's actually a pure functional language if you really look at it carefully. So if you can do SQL, why do you even need the other languages? And then we can have, in a database, we already have queries, we can have views, but now we can have incremental views for any queries you could write. And then this is actually a big one. So if you look at the streaming systems, they have custom state management. It's very hard to explain what the custom state management does. What is the semantics of such a system? They have features like, I garbage collect this state, so after some time, delete this part of the state. This never guarantees that the result will be correct, for example. So what is the result you're getting if you garbage collect the state? What if somebody will need to look at that state later? Turns out that, if you take this approach, the state is always in tables and indexes, and the system itself can take care of the state management. The system can garbage collect the state when it can prove it's no longer necessary. And you can have low latency views by computing them incrementally, and you have high throughput queries that database already provides. So that's why these systems will eat the other side of the equation. And then databases, they should offer incremental view maintenance as a service, all right? So I was listening to the talks today. This is the service you should have, okay? Including from streaming systems. I think this is a very handy system. What you do is you install a query. You say, I would like to know, for example, for my customers, I would like to have for all of them their name and then the value in their account. And then you create this as a view. You have the view subscribe to the changes of the database. So the view will monitor everything that changes in your database. But you also say, I would like to subscribe to the view. The view should tell me what's new. That's the API to your database. And now every time the database changes, the view will notify you. So you have events in, you have events out. Or you have changes in, you have changes out. And the beauty of this approach is that this is composable. Because inputs and outputs are changes, you can chain any number of these systems, and they will operate correctly. It's very, very clean. You post changes, you receive changes. So that's the way you will talk to database in the future. So if you don't believe me, go and try it. So, and if you have, you might have applications which are too expensive to run today using traditional view maintenance, or you need too low latency, or you pay too much. We'll be very happy to give you to try to solve this problem for you. So we are an relatively early stage startup, so we would be delighted, and we have great customer support. We don't have that many customers, so we do a lot of effort for the ones we can acquire. Many bugs we fix the same day you report. So I'm not promising anything, but yeah. So that's my message. It says I have 3 minutes for questions.
Yeah.
Well, yeah. Okay, so the question is about time travel queries, which we heard previously. Okay, so if you keep in a table all the events, you can actually run any queries you want. And we actually have an operator which is called the as of join. The as of join says run a join as if the left side was the table at this point in time. So that's the core mechanism which can do very efficiently incrementally, yes, which allows you to time travel queries. Yeah, so the question is, how do you represent an update to a record? So for example, when you have a table with a primary key, when you overwrite it, that actually turns into a deletion and an insertion. Yes. So there is an operator which actually will do this for you. If you declare a primary key, we'll check to see if the record is there. The input will be an update, but the output will be a zset, which has the correct deletion and insertion. Yes.